Okay, guys. I think we might have had mixed opinions about the class today because we certainly had bandwidth issues. Okay, but let's get down to it. We're on page 282, and we're dealing with transforming the sine, cos, and to a lesser extent we won't be concentrating too much on it, but the tan function as well. Okay, so what do we know is we know that sine waves like so, and that's one full period. This, if it's called the sine of x, if this is the sine of if this is the x-axis, this is 360 degrees. Okay, and this value here is 1, and this value here is minus 1. Okay, so if we just take this sine of x and think about what could we do to this function, how algebraically could we change things around. So we could add a constant. So adding a constant to a function just lifts the whole function up. It doesn't change its appearance, it doesn't change its shape. Okay, it remains congruent if you like, it doesn't change its shape, it just all goes up or all comes down depending on the constants we add. Okay, so a few observations right now though, is just before we get started, is that for sine and indeed for cos of x, the midway line, it's called, the midway line is 0, meaning it spends as much, it wobbles up and down around a 0. Okay, the period, that's the midway line, the period equals, if it's in degrees it's 360 degrees, if it's in radians that's also equal to 2 pi from here to here. So every quarter, that's a quarter of a circle. This here is pi over 2, and then 2 pi over 2, and then here we'd have 3 pi over 2 and 4 pi over 2, which is 2 pi. Okay, so that's the period. And what else can we talk about? Well, the amplitude and the range. So the range is basically how far is it from there to there, and the answer is 2. And the amplitude is 1. Okay, and then there's the characteristic shape, and later on if we add a number here we would change that characteristic shape, we just shove it left and right. Okay, but again for now I'm just going to flip that over and say, okay, so we have ourselves a wave, and it's only if you come along and say I'm going to put my origin there, it's wrong, and that's what makes this interesting. So if I put my, again you can start off with a wave, if you want it to be a sine wave you can start going up, but you know when it comes to waves, if you do enough of it you can, this is an interesting philosophical idea to really understand waves. Once I do a wave and I haven't put any scale on anything, then I can turn this into a sine of bx plus c plus d. Okay, quite a lot going on there. Okay, and that's why we're going to introduce what happens for all these numbers quite slowly. Okay, but either way, just that can turn into this. All I have to do is say what's the value. You know, if I say c is nothing, then straight away I know that this is the y-axis. If I say that this is 1 and this is minus 1, then I know that a is 1, and so on. And it looks quite complicated, so let's build it up one step at a time. Now this is where your GeoGebra helps an awful lot, because you get to see how a sine graph gets stretched or indeed shrunk. Okay, so if we want to talk about what's half sine of x, you should be able to just hand sketch saying up, down and up again. That's as much as you need for the characteristic sine. It repeats. You do that and then you say, well, how high is this? This is a half, and this is minus a half. Okay, that's a plot of the sine of x. Okay, plot 9x. Plot the sine of 9x. Okay, this is 1. Oh, my mistake. I meant to say, obviously, plot the sine y equals 9 times the sine of x. Of course we can plot the sine of 9x, but that'll come later. So plot y equals 9 times the sine of x. Up, down, up, and continue on. So I just wanted to kind of go, well, okay, what's the story? Well, the midway line is still 0. Just go midline equals 0, but we're going up to 9 and we're going down to -9. Now what I'm doing is called analysis. It's basically taking a problem and writing everything you could write about it, taking an equation and doing this graph and learning everything we could learn about it. Except, okay, it's periodic, so it goes on forever, so there would be a bit of extrapolation. But that's y equals 9 sine x. Now what does y equal -3 sine x look like? Now we got the challenge of scaling by 3, but also inverting. So, and then if I'm writing a book, which, you know, we say, okay, well, what would be the first thing I should introduce to you students, not to confuse you, or to make it the next logical thing? And that is, let's think about what does minus the sine of x look like. And of course, it's a mirror image. It's axial symmetry of sine x in the x-axis. So instead of going up, you go down, and you do that. And that's your characteristic template. And this is one of the characteristics of periodic functions. You can lift that up and drop it on here indefinitely, and you can push it back this way. You can move it by a period. 1 period, 2 periods, 3 periods, and so on. And this is -1 and 1. So talking about minus the sine of x and inverted sine of x, and talking about sine x, one thing doesn't change is the range doesn't change. The range remains the same. Okay, that's the range. The range is 2. Okay, all we've done is flipped it over. Fine. So, the next interesting thing to do is to start putting, well, let's do cos of x and in the inversion of cos of x. So for cos of x, you want to just start here and end back up here. So I didn't do a great job there. Let's go again. And maybe the idea sometimes is do your curve first. And that's all of cosine of x. That's a full period. Then think, well, your midline is in the middle. Your y-axis is here, and that's what the cos of x looks like. Okay, we know this needs to be 90, this needs to be 180, this needs to be 270 degrees, and this needs to be 360 degrees. Okay, this is 1, and the lower bound, there's an interesting phrase, the lower bound is -1, and the upper bound is 1. Can you get cosine to go bigger than that? No, not unless you start putting big numbers here. So the upper bound is 1. Can it be 1? Yes, it can. Okay. So let's invert the cosine of x. That would be saying y equals minus the cos of x. So we just want to start from a low down place, come up, come down, and come up again. So that's as much as we need for cosine of x. Those are my y-axis. Try to eyeball where the middle is. Out we go there. And this is an inverted cosine of x. Okay, guess what that is? 90 degrees. Guess what that is? 180 degrees. Guess what that is? 270, and out we go to 360 degrees. Okay, there's my angle, or whatever, x-axis, and my y-axis. 1, -1. Okay, and you must always think, to begin with, what's my shape? Then you can think about lifting it. So let's change things around here and go, and I'm sure we're going to find in GeoGebra an app that will allow us to just change these things and nothing else, to keep it keep the concept building quite in a simple way. So if I ask the question, what does y equal 3 minus the cos of x look like? What you should do is think, well, I'm going to just go up and down like this. And that's my, and you can continue on, but that's the main shape. And this is going to definitely be my y-axis. Now, where's my midline? My midline is 3. This is 3. So that's the next logical step in graphing it. Where is this? This is 2. Okay, because the gap is 1. Because the amplitude is 1. There's a number here, an understood number here of 1. And then this is up here is 4. So it oscillates up and down between 2 and 4. Okay, so the upper bound which is 3 plus 1 by the way, the lower bound equals 2. Anything else I can say? The range equals 2. Now that's interesting. So it's interesting, like you might think, oh, the big number 3 here, this could have been 11, this could have been a million. Doesn't change the fact that this thing is only adjusting itself up and down in a range of from lower to upper bound of 2. Okay, what's the period? Well, unless there's a number here, so if changing how quickly the angle changes, the period is always 360 degrees. Okay, we'll generally be either multiplying 360 degrees, if it's something like, say we had a 7th there, we'd multiply that by 7, or if we had 5 here, we would divide that by 5. That's the period. Okay, so that's that graph. I mean, you want to come along here and say that's 90 degrees and so on. It's 270 degrees and so on. Okay. And guys, the reason we're going to make this video is that really the exercises in 15.2 begin a little bit too difficult. Mind you, I'm just going to flick back to 15.1 and see what we could do. There might be some exercises there. No, it seems to skip it just doesn't ramp up from one kind of concept at a time. Now, there's nothing wrong with your book, it's just they introduce all the ideas in one go and it makes it quite difficult. I just look back to 15.1. There aren't any particular exercises there that are a bit easier, that have one concept like this midway one. Okay, so let's do another one. Let's do 5 plus the sine of x. So if I'm doing sine x, I'm going up, down, all the way down there. Notice I've come down below and back up to say, well, here. Okay, so that's a period. And I'll have my usual 90, 180, 270 and 360 degrees to think about on my x-axis. And you can say, oh, you made a mistake, you know, and that isn't, okay, fair enough, that's not my x-axis as such, my x-axis is down here. Maybe that was a mistake. Yeah, it was, okay, sorry, I'll take the blame and say, you know, there's no particular reason why a line would appear there. You can certainly put it there. But so if I'm plotting this, let's go through this again and say that's my y-axis and I'm coming off some point and I'm going up, down and up again. Okay, but now I want to think, to be honest with you, I've already raised at 5, so there's an axis down here, the x-axis. This is the y-axis. And why is it down here? Well, because this here value is, so we're going to go with 3 values, a midway value, a lower bound and an upper bound. Upper bound, let's call that a UB for upper bound, let's call this an LB for lower bound, and the midway line. Okay, so the midway line occurs at 5. The upper bound occurs at 5 plus whatever this number is, regardless of sign. It doesn't make any difference. You just add on the absolute value of this number to the midway line. Now, okay, so in this case it's 5 plus 1 is 6, and in this case this is 4. Okay. I'll try and speed it up, but I still want to just do a few more. And you work ahead of me now. So what we'll do is we'll do 3 minus the sine of x. So freeze the video, and it's free. But we use, but you hold on a second. I don't freeze it yet. And use freehand to plot this. Okay. So I'm back to you. So basically, what you wanted to do, maybe you say, well, I'm always going to have a y-axis, and until I put scale in it, I can go anywhere. Now, by going inverted, you're saying basically sine is going to come down, turn, go up a double amount if you like, compared to what you went down, and come down again. And that's your full period. Yes, it'll repeat, but we're not that interested in that. We'll have given the whole characteristic of the function in here because of the periodicity. Okay, so this number here is 3. The midline is at 3. The upper bound is at 4. And the lower bound is at 2. And all important numbers. Don't wait to be asked. Just do a full analysis. And we got your 90, 180, 270, 360 degrees. Now you don't have to mark them all in. If you say that's not and that's 360, then it is what it is. Put them in if you want to. That's plotted. Perfect. Now we could come along then and go, oh, what's the story for 30 degrees here, and in other words 210 degrees, but we have more algebraic ways of doing that. Okay, so a quick little exercise before you continue, before I cut off the video. So I could make this minus 2 plus the sine of x, and I could make this 7